last year. With we don't have physical. Don't have level of difference. Other than that, nothing is voluntary.
Oh, right. So was that last year then?
Yeah, but we also have technology right now.
Meteorology with Lewis.
Yeah,
More practical side. Right. Yeah, there's a swipe card kind of going around the room, so at some point it'll get passed back to you. If not, then just come down to the front at the end so you can swipe your card. Just a brief overview. So, talked about this yesterday really, but nothing much has changed. So, this is the weather for the week. And so we've got this high pressure and low pressure in the North Atlantic, and what that results in, if we go forward in time, is this strip of warm air being pushed, being pulled up, being wrapped around, so the warm air coming up from the south, which results in a warm front followed by a cold front. So we should expect some precipitation tomorrow as the cold front starts to come over the UK. Here. So we expect some precipitation along this cold front. After that, the high pressure dominates. So you see from Friday into the weekend, dominated by warm air being pulled up from the south. And if we look at the precipitation field, we can look at, it's a German website, so you can look at Niederschlagsum, which is the precipitation field. No, I didn't want that. I wanted that one. So this is today. You see a little bit of rain dotted around the UK. But as we go forward in time into Wednesday, you can see where this cold front is. So you can see the precipitation associated with the cold front, which then gets pushed out of the way because we have high pressure, which basically acts to block the weather. So there's high pressure at the surface, which means descending air, which creates a block for the rest of the weather. And as we see into Thursday and Friday, that tends to stop the movement of the cold fronts. So it should be fairly clear leading into the weekend. We're up to Saturday here and into Monday. And a little bit warmer too, because the air's coming from the south. Make sense? Yep. So, we've been talking about these weather forecast models, and the weather forecast models are good at forecasting precipitation. So that's one important thing that they give you. They give you how much rain there's going to be on the ground over an area. The other thing they look at is the radiative impact of the clouds. So how much radiation is being reflected back to space. And the key way in which they do that, Grates talked about how they solve the equations of fluid dynamics, so the dynamics of the air, but they also need a way of representing the clouds, because precipitation, rainfall, snowfall and so on, that starts its life as a cloud. So we need some way of describing how clouds are represented in this kind of model, this kind of numerical model. It's a weather forecast model. So I'll go into some of those details today. and we'll have a recap first. So if you remember back to last lecture, we talked about how liquid drops grow from water vapour, individual liquid drops, and we talked about what the water vapour molecules are doing. So they're moving towards the drop and they're becoming incorporated in the drop. They're condensing. And the laws that describe this process, we talked about laws of diffusion of mass and laws of diffusion of heat. Fick and Fourier describe those. Okay. And another thing that we covered is how clouds and precipitation particles are distributed in size. You remember I showed you those measurements, those aircraft measurements, which showed that the size of particles is distributed in a normal cloud, and a negative exponential distribution is quite good at describing how those sizes are distributed in the cloud. So we're going to go into that in a bit more detail today. Forget about that statement there. So we'll go into this. So we talked about the weather forecast models. So they solve the equations of fluid dynamics to describe the movement of the air based on a pressure distribution that's usually measured. So they're initialized with some data. And we have, in order to investigate atmospheric processes, we have a range of different models. And these models are useful for looking at different spatial scales. So, the resolution or the size of the domain, the computational domain, and different temporal scales. So how long you can expect to get useful information out of these models for. And these models that we use, these either weather forecast models or process scale models, there's a range of them. So they range from process-based models, so models that look at the nitty-gritty physics, small-scale nitty-gritty physics of what goes on. And these models have a spatial scale of up to, say, several kilometres, and can give you useful information on the time scale of, say, hours up to days. And we have large eddy simulation. Large eddy simulation is kind of like a CFD, computational fluid dynamics model, except it doesn't go down to the small scales, the really small scales. So the resolution typically of a large eddy simulation is around about 100 metres down to 10 metres or so. That's the grid scale, so the space in between grid points. And typically, the size of the computational domain will be several tens of kilometres. So you're looking at, up to, say, 50 kilometres. You might look to, say, simulate a cloud that has these dimensions. Then we have the mesoscale models, mesoscale. Mesoscale range up to typically hundreds of kilometres and might have a resolution of, say, 5 kilometres. That's the grid scale. So information is held on typically 5 kilometre grid scales. But now we're moving towards more kilometre scale. So individual grid points are separated by maybe a kilometre or even less as computers get more and more sophisticated and more powerful. That's probably the state of the art. This is some names of community models that we use. Cosmo, WRF, don't need to know what these acronyms are. Then we go to the global models, which are typically used for a global weather forecast. So again, some acronyms, numerical weather prediction, and these are the acronyms of some models, some community models that are used to compute these things. So global models, you're ranging to the global scale, from probably synoptic scales up to the global scale. Some of these global models can capture mesoscale effects too, if they're really high resolution global models. And it's the global models that are also used to predict climate. So you can use these models over timescales of years. And global models also, they're used in reports like the IPCC, the Intergovernmental Panel on Climate Change, to assess the effect of rising CO2 levels in the atmosphere and what that means for mankind. And part of that assessment is how clouds respond to the changing climate. So they also include some kind of, we call it a parameterization, some kind of numerical scheme that describes how clouds behave. Okay? So how do clouds behave? Well, let's think about a single cloud. So this is a picture from a field experiment in Australia that I took part in about 10 years ago during my PhD. And this cloud occurs over some islands called the Tiwi Islands. Tiwi Islands. You don't need to know this, but I'll write it down anyway. Tiwi. So these are some islands in the north of Australia, And due to their shape, when we have breaks from the monsoon in that part of the world, we get convergence over the islands, which means we get this kind of thunderstorm forming over the islands at more or less the same time every day. And it's so regular that the locals give this cloud a name. They call it Hector. Hector the convector. It's a convective cloud. Okay? So that's what it's called. So this is a picture from the Australian Air Force headquarters. It's from a hangar looking to the north at this storm, Hector. So let's just think about this cloud for a bit. So that cloud has approximate dimensions, 50 kilometres long, 50 kilometres deep, and it's about 15 kilometres high. So it goes all the way up to the tropopause in this part of the world. As Geraint talks about the tropopause. Yeah, some people say yeah. Okay, so that's the approximate dimensions. And we know that clouds typically have the number of cloud droplets, the droplet number concentration. If you were to look at a metre cubed of air and count the number of cloud drops in that metre cubed in a sample of this cloud, you'd have about 100 times 10 to the 6. If you were to look at a centimetre cubed, you'd have about 100 droplets in that centimetre cubed. So in a metre cubed, you've got 1,000,000 times more. 100 times 10 to the 6 droplets in 1 metre cubed. So 100 million droplets. So if we think about how many cloud droplets there is in this one cloud, just do like a basic calculation. 50 squared, 50,000 squared, times 15,000, times the concentration of cloud droplets, and we get that that's about 4 times 10 to the 21 cloud droplets. I hope I've got that right. 4 times 10 to the 21 cloud droplets. And we've been talking about how cloud droplets grow from water vapour. So we've been describing individual cloud droplets. So you could try and model each individual cloud droplet in this cloud and try to explain how the cloud's going to evolve in time to get some kind of forecast out. If we want to simulate the cloud that way, so we'd have to store the positions x, y and z, because it's a 3D cloud, and say the diameters or the mass of these cloud droplets. And if we wanted to do that at double precision, 8 bytes on a computer, then the number of bytes we need are 9 times 10 to the 22 bytes of memory, or 90 zettabytes. That's a lot. That's a huge amount of data. TRNA2, so this slide is probably a couple of years old now. TRNA2, this is one of the largest supercomputers, if not the largest supercomputer in the world, and it has 1.4 petabytes of RAM, which is 1.4 times 10 to the 15 bytes, which is 8 orders of magnitude too small. So that's a problem, right? We can't model clouds this way. We can't consider each individual droplet in a cloud. Does that surprise you? So we have to come up with some alternate way of doing it. So a different approach is needed. One thing we can use is so-called bin microphysics, a bin microphysics representation. So how does that work? So this is just supposed to represent cloud droplets. So we've got some kind of function, the diameter or the mass, against the number concentration. Not the number, but the number concentration. So we consider clouds at the grid scale. And what we do for the binned approach, yeah, so usually, as you should have noted from previous lectures, usually there's more small particles than there are big particles in a cloud. So that's what that's supposed to represent. So in the binned approach, we separate the diameters into size bins, so containers that contain different sizes, a representative size, D1, D2, up to Dn, and we calculate the number concentration in each of these bins, each of these size bins. That's known as the bin microphysics approach. And using this technique, it's quite accurate. So the bin microphysics approach is quite accurate. And growth theory can be used. You can't consider the growth of every single droplet in a bin, but you can consider the growth of the characteristic size of that bin. So you've got D1, you can calculate the diffusional growth rate of bin D1 and assume that this bin moves with the characteristic growth rate of that bin D1, for example. You do that for all size bins. Does that make sense? So that's quite accurate. It's still too expensive to use in an operational weather forecast models, but we do use this in the research models that we use. So I have my own bin microphysics model, which I use to do my research sometimes, and also to use in student projects. It allows you to investigate cloud formation processes in a bit more detail than they use in operational models. And the other approach is to use what we call a bulk microphysics approach. Now the bulk microphysics approach is quite cheap, it's less accurate, and typically uses two variables. So rather than using n variables, d1, d2, d, or the n times 2, because it'd be the diameters and it'd be the number concentrations in each bin, rather than using that many variables, we're representing the clouds at one grid box with just two variables. So we've got two scalar fields in 3 dimensions. That makes sense. So I'll try to explain how that works in this lecture. So the bulk approach, it uses two variables and it has some assumed shape of the distribution. And the assumed shape is usually a negative exponential. I talked about a negative exponential representing clouds reasonably well. So if this is a log scale and this is a linear scale, we can draw a straight line. And if I store the two variables, say the total condensed mass and the total number, then I can change the shape of this distribution to match the total mass and total number. So I can understand what the shape of the size distribution of cloud droplets is in a cloud with some assumed shape and just two variables. So we'll go into the details later. We'll write down some equations to understand how that works a bit better later. I guess where this kind of comes from, fairly early on, 1948, a paper by Marshall and Palmer, which made observations of raindrop size distributions and showed the raindrop size distribution to be distributed according to a negative exponential approximately. There were some things going on at the small sizes, but by and large, the size distribution is a negative exponential. And this paper was a little bit wrong. If you read some of the things this paper says, it talks about, okay, well, the reason why there's small particles is probably because as the cloud droplets start to collide and coalesce, they transfer charge. That electrical charge builds up until eventually the charge on the drop is too much. There's too much like charge on the drop, and the drop just disintegrates and forms lots of small particles. That turns out to be wrong, and we'll cover that in a later lecture. But nevertheless, the observations of negative exponentials is where this idea of bulk microphysics comes from. I'm going to skip past the slide, this one, and show the observations that I showed yesterday. So we can see approximately, we can see some negative exponential behaviour there in some part of the distribution. And also for ice particles, so that the previous slide was for droplets, but we can also represent ice particles in clouds with a negative exponential. So these are images taken from an aircraft inside an ice cloud of ice particles, and when we look at the sizes of these ice particles and count them, we get size distributions that look something like this, negative exponential. So that's where the whole idea of bulk microphysics comes from. Okay, so the aim of this lecture really is to give you an appreciation of how weather forecast models deal with clouds, how they represent clouds, and how you represent clouds in a weather forecast model. And part of the reason, as I've mentioned, well, two reasons I've mentioned for representing clouds in weather forecast models. One is the radiative effect of clouds. So by and large, clouds reflect solar radiation back to space. They have a cooling effect on Earth, but they also trap long-wave radiation. And we need to know about how that works. And also the precipitation. So how much rain you get on the surface is dependent on the properties inside the cloud. So one thing I just want to talk about briefly, because it helps with the discussion of this lecture, is an effect called the Toomey effect. So this is a paper from the 80s, 1987, and this author Toomey showed that polluted stratocumulus clouds reflect more light. And we've talked about this because we said if you increase the number of aerosol particles in a cloud, then the albedo increases. Do you remember that first lecture? Talked about that. The basic idea is the liquid water content in a thin stratocumulus cloud, as I've talked about, is determined by the thermodynamics. So we don't really need to consider the condensation process and the growth of cloud droplets. We know that by and large is going to be described by the conservation of theta Q, the moist potential temperature. But if you increase the number of aerosol particles going into this cloud, then you're going to decrease the size of the droplets because the water is shared over more droplets, so the size of the droplets decreases. But because there's more of them, the surface area to the mass ratio increases, and so the amount of scattering increases. You increase the number of particles, you increase the amount of scattering. So you increase the cloud albedo. And this is known as the first indirect effect of aerosols on clouds. So aerosols affect the properties of clouds indirectly by increasing the amount of scattering by clouds. That makes sense? Okay. And so I wanted to talk about that because that's one way in which the clouds affect large-scale variables like the radiation and the precipitation. Field observations show this kind of works. So this is some satellite data from another field project I was involved in about 5 years ago now, which was called Vocals, which was on in the southeast, over the southeast Pacific Ocean, on the west coast of Chile. So this is Chile. And in this location, the dominant meteorology is for high pressure. So there's a high pressure system that sits over the southeast Pacific Ocean. A large synoptic scale, high pressure system. And you remember I talked about if you have high pressure, it means the air is descending. But if you have an ocean, you usually have fluxes coming up. And where they meet in the middle, you have these inversions. You have a temperature inversion. Remember I talked about that? So we've been talking about it last couple of lectures, maybe. Where you have that inversion, you tend to get these stratocumulus clouds. So these very thin clouds, about 200 metres thick. And this project was looking at how air mixes into these stratocumulus clouds. So it's a satellite image. We used aircraft too. Well, this is just a satellite image looking at the cloud deck as it evolves in time. And there are some interesting features. So you can see the cloud, but you can also see some straight line features. Can you see these? Can you see these straight lines? Can you see them? What do you think they are? Ships. Someone said it. They're ship tracks. So this is just ships on the ocean emitting pollution, emitting aerosol particles. And those aerosol particles are being carried up into the cloud and acting as cloud condensation nuclei. And we see that from satellite because it reflects more radiation. So we know that this works. So that's demonstration of the first indirect effect from satellite data. Some people might think they're contrails from an aircraft. Same sort of thing, contrails from an aircraft. Aircraft emits aerosol particles and causes the air to be turbulent, which causes the cloud to form. Okay. So I wanted to talk about the first indirect effect. But scientists have been looking at this for a few years now because of the problem of rising CO2 levels. So they've been looking at a way of using this effect to decrease global temperatures, and that's known as geoengineering. You heard of geoengineering? Okay, so this particular method is known as solar radiation management, because it manages the amount of solar radiation that gets to the surface. So one idea by a guy called John Latham, who was a professor at UMIST before the merger, and is now in the US, a retired professor in the US. He wrote a paper in the 1990, about this idea of combating global warming. And the idea is to build lots of ships, and those ships will emit sea spray, so they'll take seawater and emit sea spray aerosols into the atmosphere, which will increase the reflectiveness of clouds, and that in turn will reflect more solar radiation. What do you think about that? There are some ethical challenges there, shall we say. But I'll talk a bit more about it. So it has moved on from the 1990s. I've done a little bit of work on it, just more theoretical stuff. I've not actually done anything to the atmosphere, but I can say a few words about this in just a moment. So there's a paper in a journal called Philosophical Transactions of the Royal Society. So this is out there now. If you're interested, you can look at that paper. There's a few more papers on this too in the same journal. And part of this paper looked at how this geoengineering could affect something like the Arctic sea ice amount. So the Arctic sea ice amount, decreasing levels of Arctic sea ice is a known problem due to global warming. So there are two simulations here, global simulations, so this is a global simulation. And it also has a simulation of the atmosphere, but it also has a simulation of how the atmosphere interacts with the sea ice and the oceans. And it's the Met Office Hadley climate model, by the way. So on the left, this is looking down on the North Pole. We've got the difference between the sea ice height in the year 2090 for a doubling of CO2, so we double CO2 from current levels, or if we keep it constant. And you can see there's a decrease in the level of sea ice if we're to increase global CO2 levels, we expect the sea ice level to go down. Goes down by about 0.3 metres, probably an underestimate to be honest. If you include geoengineering, so if you increase the reflectiveness of stratocumulus clouds by this method that I've just talked about, then you can stop some of this decline in the Arctic sea ice. So this is a numerical model that scientists have done to try and justify this geoengineering effect. Any thoughts about that? So, I'm personally against it. I did some quick back of the envelope calculations to show. So, the method this works is to force sea spray through a small nozzle. And you can, and the nozzle has to be really tiny. And these nozzles haven't been made yet. And you can do a quick back of the envelope calculation to work out how much work is required to force seawater through these nozzles. And you can do a back of the envelope calculation to say how much sea spray you'd need in the atmosphere to get the effect you need. And the cost, the energy cost involved, far outweighs the benefit you get. So I think you need some kind of cost benefit analysis. I've not published that yet, but these are some of the reasons why I'm against it. And no one seems to be doing that, which is quite interesting. Saw something on, I think it was LinkedIn today, which reminded me of this. So it's this idea of using graphene as a sieve to desalinate seawater. Have you seen this? And again, that involves forcing seawater through these graphene sieves, these molecular sieves. And I just can't for the life of me see, how that's energetically favourable, because the amount of energy you need to force seawater through these sieves is just, it's just huge. So I don't know whether that's been done yet. I'd be interested to see over the next few years whether these molecular sieves are actually viable as a desalination idea. So watch this space. Anyway, so I'd just like to. Okay, so that's the lecture more or less. I want to write down a few equations now to show you how this works in practice. So, what do you do? So the key thing you need to take from this lecture, the ideas, the ideas I've been talking about, but the quantitative bit that we need to consider are that particles are distributed in size and weather forecast models use this idea of bulk microphysics, and we need to know about the idea of moments. So this is new, moments of particle size distributions. Are you familiar with the idea of a moment of a distribution? The moment of a distribution? Yeah. Physicists will have probably considered, is it Maxwell-Boltzmann distribution, where you calculate the characteristic velocity of a molecule by multiplying v by a distribution and doing an integral. Familiar with that idea? Very similar idea here. So, for example, the 0th moment, I'll call it m0, of a particle size distribution is the integral from 0 to infinity of dn by dd, which is a function of diameter. N is the number, d is diameter. And I've said that this function dn by dd is a negative exponential. So this represents the sizes of particles in clouds. So the 0th moment is this. Last lecture, we derived the growth rate of single cloud drops So I'll call that dm by dt. The mass growth rate, so this is last lecture, and we found that the growth rate was equal to a constant multiplied by the diameter. So I wrote this down as 4 pi, I think it was radius actually, radius divided by this thermodynamic constant. Do you remember that? So this is for a single cloud drop. So if I was to calculate the integral of A times D, dn by dd, from 0 to infinity, A times D, dn by dd, and this is proportional to the growth rate of all cloud droplets in the distribution. So AD is the growth rate of a single cloud droplet. Multiply this by the distribution and integrate, and that's proportional to the growth rate of all cloud droplets in the distribution. Does that make sense? So this can be written down as the condensation rate. And that's the start of how these bulk microphysics models work. So we're representing the cloud with two variables, the number and the mass. If we want to know how much condensation there is, then we just need to calculate, essentially, it's the first moment of the distribution because it's d multiplied by dm by dd. So this would be the first moment times a constant. So you can see how moments of the distribution are useful. So the growth rate is proportional to m1 in weather forecast models. So then the next point is that these distributions are represented with negative exponential. So what that means is dn by dd is equal to, and there's usually a constant which we call the intercept, e to the minus lambda, which is usually called the slope, and d. So this is how we represent the cloud distribution. It's a negative exponential. And the reason why we use a negative exponential is because it's based on observations, but another useful property of this negative exponential is that we can easily calculate the moments of a negative exponential. So any moment of this negative exponential we can calculate analytically. So I'll write that down now. So the integral of n0 times d to the mu, where mu is an integer, times by e to the minus lambda naught d is this. So that's n0, which is a constant, mu factorial, divided by lambda naught, which is a constant, to the power mu plus 1. So that greatly simplifies the calculations we make in a weather forecast model. Because we don't have to integrate anything numerically. We can just write down the analytic form of things like the growth rate, precipitation rate, the radiative effect. So we calculated the mass growth rate of the distribution by using this idea of moments. The other thing I want to consider is the radiative effect of a cloud. So let's do that now. So first of all, using this equation, I can write down m naught. So m naught would be 0, mu is 0, so mu factorial would be 1, because 0 factorial is 1. So m naught is just n naught over lambda. Now m naught is the total number in the distribution. It's the total number, 0th moment. m1 is n naught, 1 factorial is 1, divided by lambda naught squared, mu plus 1. Remember, m naught, total number, m1 is proportional to the growth rate of the cloud, depending on what the supersaturation is. Now I'm going to pluck something out of the air. I'm going to tell you that the albedo of a cloud is, there's an approximation for this. We could go into the theory of it all, but I'll just write it down and justify it. So the cloud albedo, the amount of shortwave radiation that a cloud reflects, is approximately equal to, so there's a pi in there, there's an m2, which is the second moment, and there's a delta z. So we've got a cloud layer which is delta z thick. It contains particles, obviously, divided by, and it's pi m2 delta z plus 15.4. So this is an approximate equation for how much shortwave radiation is reflected by a cloud. And this is approximately equal to, because 15.4 is much greater than, this term is much greater than this term, so this is approximately equal to 15.4. So it's approximately equal to this, because 15.4 is usually much greater than this term. So that tells us that if we plot a graph of the second moment in this cloud for a constant depth of the cloud albedo, it's just proportional to the second moment. And that makes sense, because the second moment is proportional to the surface area of the cloud drops, the projected area of the cloud drops. And that's what the radiation interacts with. Okay, so you've got cloud droplets, radiation interacts, it sees how much surface area, projected surface area there is in the cloud. So, and it's the interaction with those drops that causes the scattering of the light away from the surface. So it makes sense that the cloud albedo should be approximately proportional to the second moment. Okay, so we've defined first moment as being proportional to the growth rate, second moment being proportional to the albedo. Now I want to talk about geoengineering and how that works. So for the exam, you need to be familiar with manipulating these moments of the size distributions. So you need to be able to do the integrals and also, you know, go through things like deriving what I'm about to derive now, which is about geoengineering. So geoengineering. So remember, thin layer cloud, the thermodynamics defines the liquid water content. Because it's approximately in equilibrium. M naught is equal to N naught over lambda naught. We'll call that equation 1. So this is the number of cloud drops. M3, which is the mass inside the cloud, the condensed liquid water. So 3 factorial is 6. n naught divided by lambda naught to the power 4, because it's 1 plus mu to the power 1 plus mu. That's equation 2. Divide equation 1 by equation 2, and we can find that lambda naught is 6m naught over m3. That's equation 3. So I talked about my weather forecast model having two variables, the total number, which is m naught, and the total mass, which is proportional to m3. And from these two variables I can calculate the slope of the distribution. So I can get my distribution parameters from these two variables. Sub 3 into 1. So the intercept then is m naught 6 m naught over m3 to the power 1/3. So now I've found the intercept. So from my two variables I can calculate the intercept and the slope, which allows me to calculate any other moment of the distribution. Once I know the intercept and the slope, I can calculate any other moment I want. I need to know the intercept and the slope. Intercept and the slope, and I can calculate any other moment I want. So I can calculate m2 now, which is what I want, to calculate the radiative effect. So now I've got the intercept and the slope, I can calculate m2 using my moment equation, that thing with a factorial in it. m2 turns out to be 2n naught divided by lambda naught cubed. And substitute the equation for n naught and lambda naught in here to find that m2 is equal to, so this is just algebra, 6m naught over m3 to the 1/3 times 2 divided by 6m naught over m3. And what we find, if we work out what the numerical values are, we find that m2 is approximately equal to, and the constant in the front is 0.657, and it's m naught to the power 1/3 times m3 to the power 2/3. So the second moment is proportional to m naught to the power 1/3 and m3 to the power 2/3. Now I'm considering a cloud where the mass inside the cloud stays constant, but I can just alter the number of cloud drops. So I'm going to hold m3 constant and look at how it varies by changing the number of cloud drops. So this is number of cloud drops. And this is m2. And it looks, because it's to the power 1/3, it looks something like this. So what does that tell us about geoengineering? That tells us something useful. It tells us that the amount of radiation that we can expect to reflect from a cloud depends on what the background aerosol is. Why did it tell us that? Well, if we start in a clean environment, we're starting with M2 already quite low, because the number of aerosol particles will be quite low, hence the clean environment. If we add more aerosols, then we can change M2 by quite a bit, gradients higher. If we start in a polluted environment, then we can't expect to get much change in M2. Does that make sense? And because M2 is proportional to the albedo, then depending on which environment we start in, that's going to govern how much change, how much more radiation we can reflect back to space. That's the key point. On an exam, you might get a question, explain with reference to equations why geoengineering is only effective in a clean environment. Okay? So I'd expect you to be able to do something like this. You'd get all the you get the moment generating equation, but you'd be expected to work through this and give a quantitative argument as to why that might be. Okay, probably got a couple of minutes. So I've covered the first moment being important. So the first moment's important to the growth rate. I've covered the second moment being important. The second moment's important for how much radiation is reflected by a cloud. I'm not going to cover other moments today because I've run out of time, but I'll cover that next lecture. And I just wanted to go back to the presentation and show you another couple of slides before we finish off. So, I don't want to explain the top plot. I'll explain this bottom plot. What this is a calculation using a process model saying that if we add sea salt particles of different sizes, different masses actually, to a cloud and of different number concentrations, what albedo change, what cloud albedo change would we expect to get? And so for this case, this is in regions of low aerosol concentration, so this is in a clean environment. We can expect to get a huge change. So the larger the particles, the larger the albedo change. Up to 40%, that's a change of 0.4 in the albedo. Means that you look at the fraction of solar radiation that's reflected, you can reflect up to 0.4 times the incoming solar radiation back to space in a clean environment. Okay? In a polluted environment, it changes a bit, so we're only getting up to 10% change, and we have to add really large aerosol particles into that cloud. Forget about the top plot, I haven't got time to explain that. But the other important thing is if you, in a polluted environment where the aerosol concentrations are already high, if you add in large aerosol particles of a low concentration, then they preferentially activate into